Hello. In this session, we'll be looking at the Python implementation of value iteration for the numerical example discussed in the lecture. So here we can see that the problem setting is having a fixed cost of 4, variable cost of 2, carrying cost of 1 per unit per unit per time period, salvage cost of 0, revenue of 8 per unit sold, and inventory maximum limit is 4, time horizon is 3, discounting factor lambda is equal to 0.95, and the demand distribution is when the probability of having demand equal to 1 is 1 by 4, demand equal to 2 is 1 by 2, demand equal to 3 is 1 by 4, and all other demand values it is 0. So let us look at the Python implementation. So here we are importing the Python package here, and here we are giving the problem setting details as mentioned in the lecture. Here we are having the inventory limit M, maximum order as 5 as presented in the previous problem, lambda equal to 0.95. And here we are defining the probability distribution and the demand values. So the definition of immediate cost remains the same as to the Bellman equation implementation. And here we can see that the reward. So the reward, what all depends upon the reward depends upon what all variables. It depends upon the current state, the current action, and the next state. Of course, the next state is dependent upon the demand that has realized at that instant, because demand is a random variable now. The next state can be anything, and because of that, the when the next state is a different value, it means that the carrying cost can be different, because the carrying cost is directly proportional to the next state, and so the reward will also be stochastic in nature. It will not be static. So let us calculate the reward. To calculate the reward, we need revenue, we need immediate cost, and we need the carrying cost. So revenue is equal to the overall quantity sold. How do we calculate the quantity sold? Quantity sold is nothing but current state plus current action, which is whatever we have totally which is a supply that we have, and the next state, if we subtract that, and the difference between these two things is the quantity that was outflown between time t and t plus 1, which is nothing but the quantity sold. And so that is quantity sold, and so the final reward is nothing but quantity sold into revenue per unit, that is $8, minus immediate cost of making an action, minus the carrying cost next state into the carrying cost per unit time per time period. So this is the overall reward when we transition from a current state to a next state by making an action A. Now let's calculate the transition probability matrix, or for given current state, current action, next state, we need to calculate the probability. Now as you can see in the lecture, as you can see in this lecture, if the next state is greater than s plus a, current state plus current action, but less than the inventory value, then this is theoretically not possible, and so this is 0. And if the next state is between 0 and s plus a, and s plus a is less than or equal to the inventory value, then it equals to the then what is it is equal to the demand value, the probability of having a demand of s plus a minus s dash. That's the demand for this region, and so that is the probability. And for the third case, where if s dash is equal to 0 and s plus a is less than or equal to m, now so next state can be equal to 0. That means that either the demand could have been met, or the demand could have been partially met in the sense. So we need to make sure that we are considering all the probabilities where the demand is at least greater, the demand, we need to add all the probabilities where the demand is greater than the maximum quantity that we can supply, that is nothing but s plus a. So this is the probability, and the same thing has been coded here. Here you can see when d is equal to current state plus a minus next state, that is the second case, and this is the third case where the demand is greater than current state plus current action. We take all such probabilities where this condition is satisfied, and we take the sum of it. So to show an example, let's say we are in a current state 1, and we are doing a current action of 0, and then the next state is 0. That means that When the next state is 0, it directly goes to this step, correct? Because the next state is 0 and the current state plus current action is less than or equal to m, because the value of m is 4, which is true in this case because 0 plus 1 is less than or equal to 4. And in this case, we need to sum all the probabilities where the demand is greater than current state plus current action, which is nothing but 1 plus 0 1. So if you look at the d, it is so this condition is satisfied for 2 and 3, and if we sum the respective probabilities, it's zero point 0.5 plus 0.25, which is 0.75, and here you can see that the result is 0.75, and here you can see that the result is 0.75. And let's now look at the uh, let's now look at the value iteration logic. So the value iteration logic looks something like this. We need to arbitrarily initialize the value for every state, and then we need to run a loop where we are going to iteratively update the value iteration function. And how are we going to update it? We are going to update it based upon the uh, Bellman equation. So how are we going to do it? As presented in the Yes. So as presented here, we will be taking a random vector as a initialization for the value function, and we'll have a threshold epsilon. Now we will try to update the value function by using the Bellman equation, which is nothing but this expression. Since the reward is also the reward is also stochastic, we need to add the reward to the value iteration and then multiply it by uh, uh, the probability transition matrix. Here you can see that we'll take the nth step value iteration value and try to calculate the n plus 1 step value iteration value. And when the difference between n plus 1 and nth step value iteration is less than epsilon, we break out of the loop and we have obtained the stable value function for all the possible states. And once this is obtained, we can calculate the corresponding policy by using the argmax expression over the value function over the value function value. So here we will look at the logic. So we are having a, here if you see, we are having a cutoff, right? Lambda, the difference between the current state and the next, we are having that calculated here. So here you can see this is the policy evaluation, which will come back a little later. So here we will see the value iteration process. So what we are doing, we are initializing a random variable, random random vector as the initial value vector. We are having a counter to calculate how many iterations we need to converge, and this is the epsilon that we are going to provide. Okay, and so here, while true, counter equal to counter plus 1, we are getting the action space here, and then we are creating a dummy variable to save the vn plus 1 vector. And for every state s, what do? We try to pass through all possible actions, and all possible actions, for every action you will have different possibilities of going to calculate the overall reward. So here you can see reward plus the initial value vn into lambda, and that everything multiplied by the transition probability. Here we are multiplying the reward also by the transition probability, because the reward is also probabilistic in nature. And it is the same logic that we followed in the Bellman equation. But here, since we are trying to maximize the entire profit, or the we are trying to find the maximum value. And so once we found the best value, which is the maximum possible value, we save it as a new value, and we again we try to calculate the distance between the current epsilon and between the current value and the new value. And if it's less than epsilon, we we print the new value and break. Else we initialize the new value with the updated value vector, and then we continue the loop. So to give an idea of how this works, let's try to print for all possible iterations. So let's look how this logic runs. So here you can see the value iteration runs. Here you can see the random initialization for the value functions is 2.15, 6.46, 6.15, 9.04, and so on. And here you can see that the value iteration performs, and after a point the values become a little stable, but still the values do not come under the condition of the difference between the values does not come under epsilon. So still the iterations proceed, and and at 157 iteration we can see that the for the while loop has broken out because of the condition being satisfied, and this is the stable value vector for the given problem setting. And from this, so now we know now we know the value function. From this value function, how do we calculate the policy? Now the calculating policy is pretty straightforward. Here, to calculate the epsilon policy, because we have given a threshold of epsilon here, we are calling it as an optimal epsilon policy. We need to find, for every state we need to find the action, whichever action produces the uh, biggest value function, whichever action specific action produces the biggest value function. So that's what is presented in the top in the value function logic. So in the policy evaluation logic, so policy evaluation will take a value vector, and what it will try to initialize a zero policy, and then for every state s, it will try to calculate the best action by looping over the actions and trying to calculate the overall value function using the value functions of the other states. And once this is performed, whichever action has the best value, it will be taken as the it will be taken it will be taken as the best policy for the current action. So depending upon this logic, and after we pass the converged, so here we can see that the new value, if it passes out of the loop, it is the converged value vector. And here we are passing the converged value vector to the policy evaluation function. And if we try to look into it, so the policy evaluation vector is this. So how do we interpret the policy evaluation vector? So we evaluate. So how do we understand, first of all, how do we understand the value vector itself? So the possible values of state S are 0 to 1, 1, 2, 3 till m, because the maximum inventory value is m. It can have a minimum value of 0 and a maximum value of m. And so the value of 0 represents the value of state equal to 0. The value of 1 represents the value of state equal to 1, and similarly for the policy also. So how do we interpret the policy? So whenever the state value or whenever the inventory value is 0, make an order of 4. Whenever an inventory value is 1, make a value of 3. Whenever the inventory value is uh, 2, make an order of 2. And whenever the inventory value is 3, make a value of 1. So the indexes of this array are the state values, and the values in the array correspond to the optimal option we need to take